Welcome to part 2 of this video lecture, automobile diesel piston engine brake horsepower, foot-pounds torque, and brake thermal efficiency calculation. We will now move on with this video lecture focusing on how to calculate the percent brake thermal efficiency of this particular 4-stroke diesel piston engine while powering this particular automobile when at cruise speed on dry level paved road at an MPG fuel economy of 45 miles per gallon. Assume that this car is driving in the following environmental conditions: vehicle cruise speed 70 miles per hour, air temperature the car is driving through 65 degrees Fahrenheit, and elevation above sea level 940 feet MSL above sea level. First thing we need to do is calculate the atmospheric pressure in PSI between the elevations of sea level to 36,089 feet above sea level. You can use this formula to mathematically calculate the atmospheric pressure in pounds per square inch. All you do is take the elevation above sea level, divide it by this value, and then subtract it from 1, and then this whole quantity, you then take it to the 5.255876 power. When you're done, you're going to get a coefficient. You multiply that times 14.7, and that translates to an accurate mathematical calculation when at 940 feet above sea level, an atmospheric pressure of 14.2 psi will exist. Once you get that value, you need that to calculate the air density in slugs per cubic foot at given atmospheric pressure and temperature in degrees Fahrenheit. What you must do is take that degrees Fahrenheit and convert it into absolute Rankine's temperature. Rankine's temperature scale is the absolute temperature scale relative to the Fahrenheit scale only. So all you do is take the degrees Fahrenheit of the air temperature and add 460. This will allow you to calculate the absolute temperature of the relative degrees Fahrenheit scale. So when we do so, we get 525 degrees Rankine. This is the absolute temperature of 65 degrees Fahrenheit. So now we use this formula here, the atmospheric pressure in PSI times 29 times 0.031. Take that quantity and divide it into the ideal gas constant for air, which is 10.73, times the absolute temperature in degrees Rankine. When we do so, we get an air density of 0.00227 slugs per cubic foot when the vehicle is driving in 65 degree Fahrenheit air at an elevation of 940 feet above sea level. Now, the car is finished accelerating. It is now at a steady cruise speed of 70 miles per hour. No acceleration, no deceleration. So the only forces that are opposing the automobile's inertia are the aerodynamic drag exerting against the car's frontal area and the tire rolling resistance. So these are the two forces the car's engine has to overcome in order to maintain a steady zero acceleration cruise speed of 70 miles per hour. So what we need to do is take the data that we've computed, the air density, we can now plug that into the formula required to calculate the power to overcome aerodynamic drag in watts. That would be the car's drag coefficient times the slugs per cubic foot air density times the vehicle's projected frontal area. We're approximating 16 square feet of the car's projected frontal area, and then the speed of the car in feet per second cubed divided by 2. When you do that, you will get the watts power required to overcome aerodynamic drag. This can then be divided into 746, the number of watts to horsepower, to calculate the horsepower to overcome aerodynamic drag. Now the power to overcome tire rolling resistance is the weight of the vehicle in pounds times the speed of the vehicle in feet per second times the coefficient of rolling resistance for automobile and light truck on paved dry road, which is 0.012. Now we have all the data to figure out what kind of power is required to keep the car moving at steady cruise speed on dry, level, paved road. So all we do is we take the drag coefficient for this car, 0.3, multiply it times the air density in slugs per cubic foot, times the projected frontal area, approximately 16 square feet, times the feet per second conversion of 70 miles per hour, which is 70 times 2215, so it's 102.67 feet per second cubed. This value, this whole quantity, then divided by 2, so 5,896.13 watts of power are needed by the engine to overcome the aerodynamic drag. So we divide that into 746, that translates to almost 8 brake horsepower, 7.9 to be exact. So the next component to figure out the power to overcome is the tire rolling resistance, and that's simply just the weight of the vehicle in pounds, 3296, times the speed of the vehicle in feet per second, times the coefficient of rolling resistance. That would be 5,414.4 foot-pounds per second of power is required to overcome the tire rolling resistance. There's 550 foot-pounds per second to 1 horsepower. Since we're not using watts, we're using foot-pounds per second, you need to use 550 instead of 746. Divide those out, it's about almost 10 horsepower to overcome the tire rolling resistance. 9.85 to be exact. So when we add it together, it's almost 18 brake horsepower to keep the car moving at steady speed at those given environmental conditions. So now we're ready to figure out what the overall percent brake thermal efficiency is by taking the BTU energy content of the fuel, 19,300 BTU per pound, and fuel density of 7.1 pounds per US gallon, which is the heat energy content and fuel density of diesel fuel. Then we know that 1 BTU per minute in the form of heat from burning fuel is 17.6 watts, also equal to 778 foot-pounds per minute, or 0.0236 horsepower. That is in the form of burning fuel. So then we calculate how much fuel consumption takes place over an hour, assuming that the car is driving at 70 miles per hour for 1 hour continual speed. So that's 70 miles distance divided by 45 miles per gallon. So in an hour time, it's 1.55 US gallons of diesel fuel consumption at that MPG and cruise speed values. Then we calculate the actual pounds per hour diesel fuel consumption, 1.55 US gallons times 7.1 divided by 60, so there's 0.184 pounds per minute of diesel fuel consumption going on. So now all we have to do is get a ratio between the power input, that's the power output, which is 17.75 brake horsepower in foot-pounds per minute. So we multiply it times 33,000, and we divide that into the power input in the form of burning fuel. So that's the ppm, 0.184, times the BTU per pound, heat energy content of the diesel fuel, times 778, the number of foot-pounds per minute to 1 BTU per minute. And we divide it out and multiply it times 100. Under a load at 70 miles per hour, we have an overall percent brake thermal efficiency of 21.2%, which is much higher than the gasoline 4-stroke piston engine on a similar car traveling at 70 miles per hour, which is right around 15 to 16%. So hence you get a higher mile per gallon fuel economy due to the fact the compression ratio is so much higher in the diesel, you can squeeze more energy out of the fuel. The only drawback is that the diesel 4-stroke piston engine doesn't have the acceleration that the 4-stroke gasoline piston engine does, but it does have the payload hauling capacity at a higher effectivity than the 4-stroke piston engine, because the pressure exerted on the piston during each power stroke is substantially higher than the 4-stroke gasoline piston engine, allowing for more torque to exist at lower RPM. So overall, the given vehicle has about a 5 to 6% higher brake thermal efficiency than the gasoline 4-stroke piston engine of a similar vehicle. Although the most advanced diesel 4-stroke piston engines in the world rely on computer-controlled air-fuel ratio software advancements, also causing higher efficiency to the variable valve timing, high-low cam lobes, fuel rail systems, and certain higher value 4-stroke diesel piston engines can operate under no load as high as 50% overall brake thermal efficiency when at idle and the vehicle is parked, and then they operate as high as 38-39% while on the road. And that would be a very high-end diesel 4-stroke model. Many GM Volvo makes operate on these very expensive applications, but for the high quality you get at the decent price of a 2015 Volkswagen Jetta, you get quite nominal and satisfactory performance, power, quality, and MPG for what you pay for. So this is a quite high quality Volkswagen. For the amount of money you pay, you get quite a lot of return for your fuel economy. So we've proved mathematically, based off the OEM certified specifications, what the actual the typical automobile diesel piston engine using a 4-stroke cycle, brake horsepower, foot-pounds torque, and brake thermal efficiency is when utilized in practical applications on the highway at typical driving speeds. Thank you for watching this video, and have a great day.